Hello and welcome to this tutorial on building your first neural network using PyTorch. PyTorch is a great Python library in the sense that it is extremely simple to use and does all the heavy lifting by itself. When you define a neural network from scratch in Python, let's say, you need to build functions to do all kinds of tasks, including updating the weights and the bias, as we saw in the last lecture. And this often proves to be a difficult task. When you use PyTorch does all of this computation for you. So you just need to write a few simple lines of code and PyTorch does it all in the background. So let's get started with building our first neural network. The first thing to do is to import the libraries. We import torch, torch.nn.functional as f, torch.nn as nn, and we execute that. The next thing to do is to define a class for our neural network. So let's define a class net which inherits from nn.module, and we define a few functions in this class. The first function will be the init function, and here we put down this line of code. The next thing to do is to define the model's architecture that we'll be using, and as we saw in the last tutorial, we want our network to have two layers. That is, it starts from a vector of 4 numbers. It is linearly fully connected to an array of 3 numbers, and then it goes to the output, which is just a single number. So the first thing to do will be to define a linear combination, that is a fully connected layer essentially, and we put in the inputs as 4 and output as 3, 4.3. After which the next thing to do is self.fc2. So fc stands for fully connected. So this is the first fully connected layer and this is the second fully connected layer. nn.linear, this is the syntax for declaring a fully connected layer, and this goes from 3 to 1. That's it for the architecture. Let's define the way our network will go through this architecture. So we define a function that is forward, which is essentially forward propagation, which is taking the initial input and multiplying it by the weights and going on up till the output to predict an output. And this will happen as follows. If we have x as the input given to this forward function, we update x as f.relu self.fc1 of x. Relu stands for the non-linear function, which is a rectified linear unit, and the graph of this function is essentially linear for x greater than 0 and is exactly equal to 0 for x less than and equal to 0. So the graph looks like flat on the x-axis up till x equal to 0, and then it goes on to be a straight line with slope equal to 1. So this is the first thing that we'll do. We multiply it through the fully connected layer, first layer, and then we take the non-linear function and apply it on that, on the input of the first layer. The next thing to do is to pass this through the second layer and then take the nonlinear function through the output of the second layer. So self.fc2 of x, and ultimately we want to return x. So let's define an object of the class that we created, which is now called net. So this is what our net looks like. Our neural network, it has a linear layer, in features equal to 4, out equal to 3, and the next layer is 3 and 1, and we have a bias term for each of these. Let's train our neural network now. Let's just train it on random values for now, because we aren't dealing with actual images or anything of that sort. So we'll declare a random vector torch.randn, and let's say that we have 100 training examples, each of size 1 and 4. Let's also define a random target which has the actual ground truth values, and let's say that all of those values are integers. Let's make this And now the next thing to do is to declare a criteria, that is a loss function. So we need to define a measure that calculates how much we deviated from the actual ground truth values while predicting an output for a given set of inputs. We need to quantize that, the amount of deviation that we see in our model when it predicts an output given a set of inputs. So that is defined as, this is the mean squared error loss, and it stands for a particular type of criteria where the loss is calculated as the difference between the actual value and the predicted value and the square of that, and all of these are summed together. Next, let's define the learning rate, which is an extremely important hyperparameter when training neural networks. We also declared the number of epochs, which is the number of runs that our neural network will take through the entire data set that we have. If you're curious and want to know more, you can visit the links in the description to learn more about the inner workings of neural networks and all of these parameters. But for now, we'll focus on building a network and what are the important parts that need to be coded in order to build a neural network. So next, let's iterate over all of our epochs, which are 100 epochs. So for an epoch in range of epochs, let's declare the losses equal to 0.0, which is the net loss. Let's also initialize the gradients to 0. So the gradients which essentially determine how the weights and the bias terms get updated by what values. We initialize them to 0 before starting every epoch. We then perform forward propagation, which is we declare output to be net of the inputs. This is the syntax for forward propagation. So you pass in the inputs through the net and you get the output as the result. Let's define the predictions that our neural network makes, and we need to round the output because our target is an integer. And then we can declare the loss as criterion, which was our MSE loss, nn.mse loss of output and target. So output was what we obtained by forward propagation in this step, and target is the actual ground truth value, which is the correct label. Losses plus equal to loss. We define the accuracy of our prediction in this step as the sum of all of the values that it got true, and then we perform the updation of parameters using the backward propagation step, losses.backward, and we just update our values for weights and bias using a for loop. For f, we subtract the value of .grad.data times the learning rate, and we get the result right. When we start from the first epoch, the accuracy is 47% and the loss is 0.834, and as the model trains on this data, the accuracy decreases sometimes, but on the whole it keeps on increasing, and towards the end it increases by a lot and goes up to 56. So that's not too bad, and the loss keeps on decreasing on each iteration, and initially it was really high, more than 0.2662. So the loss keeps on decreasing and the accuracy keeps on increasing as the model is trained over several epochs on the training data. That's how you can build your first neural network using PyTorch. And thank you for watching. I'll see you in the next video.